Can you hear me? Cool. All right. So, another talk, this time on peer-to-peer hole punching without any centralized infrastructure. Like a big title here. I'll go into a bunch of what that means. Well, first of all, why will we need hole punching, right? No one wants to do hole punching. Then how can we do that in a peer-to-peer fashion? And most importantly, how can we not depend on any centralized infrastructure in the end? Cool. Small introduction. You already heard that yesterday, probably. I'm Max, software engineer at Protocol Labs, stewarding the libp2p project with a bunch of other people here, mostly working on the Rust implementation. You might know me from a past life around Prometheus and Kubernetes. And yeah, you can reach out to me directly, but I'll share a bunch of sources where you can reach out in public to the whole team and the whole community, whole project, so on. Some graphs a little bit small. If you want to, I upload the slides here. We can probably share the slides via the organizers in the end as well. So in case that's helpful to people, leave that open for a couple of seconds. Small disclaimer, hole punching is really complex, and it's not complicated, it's complex. So there's a lot around, a lot to learn. I'll simplify a lot of things, and I think that explains better what the motivation behind it, and you get the greater picture. But then I'm happy to go into concrete details, probably best after the talk or through questions and so on. So we can do that later on. All right, libp2p, you heard a lot about libp2p, modular networking stack, composable building blocks, specified and implemented in many languages, running pretty much anywhere. We might even have a lightning talk on that towards the end. Many networks adopting it, and then hard to measure, but a bunch of nodes out there online at any given point in time. Cool. OK, so hole punching. Let's go a little bit first into why we would need it in the very first place, right? And hole punching is mostly a technique you would use in the wider internet. Obviously, you can use it in LAN networks as well, but usually you don't need to overcome firewalls and NATs in those scenarios. In general, we have the little problem that when you're in your home network, let's say with your laptop, there's something disconnecting you or connecting you, but like we have a barrier between you and the wider internet, and that is your router, right? Router does a great job, it's really important, but it acts as a firewall and a NAT in most scenarios. Okay, what is a NAT? There are many different kinds of NATs. NATs as a network address translator. Put in very simple terms, it takes your local network IP address and maps it to a public IP address, right? And then people see you under that public IP address in the wider internet. All right, what is a firewall? Basically, a firewall, the most basic functionality of firewall, obviously there's a lot more to it, is it doesn't let any packet in unless a packet to that destination went out before. Right? So nothing comes in unless something went out before. And that is done via state tables. Basically, if I send a packet out, my router will simply add a 5-tuple, it's called, of the source IP address, the destination IP address, the transport that I'm using, and then the source port and destination port into its most routers call that state table. And then when something is trying to get into the local network, the router checks the state table, or the firewall checks the state table. And if there's an entry there, it will let the packet go through. Cool? All right. So why is all of this a problem? Well, first of all, don't go deactivate your firewalls. Please don't do that, right? Also, NAT is important in the IPv4 world. Some people say it's important in the IPv6 world, but that's a different story. So don't do that. It's very important that no attacker can just reach out to your local machine, right? So, but how is that a problem in the peer-to-peer world? Well, we want to laptops, for example, in 2 different local networks to be able to establish a direct connection, right? And I brought a small example here, beautiful flowcharts. We have A and B. A wants to connect to B, and B wants to connect to A, right? Both are in their own local network. They're both behind their router. And now if A tries to establish a connection to B, A sends a packet via it's routed via its router A to router B. Router B will check in its state table, will not find a 5-tuple, and then drop the packet, right? It simply says, like, nothing went out first, so I'm not going to let anything in. And the same for B. If you send the packet and so on, router A would check its state table, no 5-tuple in there, drop the packet. Okay? So that's not how you establish connections. Like, that's not going to work. Before you do hole punching, you should probably try everything else. And one thing is, for example, UPnP. Basically a protocol to allow you to talk to your firewall and say, by the way, I'm happy if something comes in from those addresses, or route them to me. It's fine. You can go to your router and manually configure a port forward if you want to do that, and if you know how to do that. And then lastly, you can relay all your traffic. So let's say in this scenario, we would have some node in the middle, and that node would relay all the packets between the 2 peers. Okay, so first 2 options, cool. UPnP is not available everywhere. Manually opening a port is a lot of work, or it needs technical expertise. And then relaying everything, you need a relay node. That's expensive. You need egress and ingress for the relay node. And lastly, you have additional latency, right? Because you have an additional hop in your path. Cool. All right, so what we want to do instead, or in case none of the earlier options work, or in case relaying is not an option, we want to do hole punching. And I'll go quickly into how that works in a, again, simplified way. Let's assume we know each other's addresses. So we ignore NATs basically for now and only look into firewalls. And let's also assume that we have some magical mechanism for A and B to start connecting to each other at the same time, right? Time synchronization, super difficult. So let's just assume we have that, right? So A would send a packet out. It would be routed to router A. And, well, B would roughly around the same time do the same, right? Now, a packet A to router A means that a 5-tuple is added to its state table to router A, right? So we have this event here. And the same is happening on router B. Then the 2 packets cross paths somewhere in the internet, right? They don't actually cross paths, but it's, I think, a cool thing to think about. They say hello to each other, and now packet B comes to router A. Router A sees packet from B, checks its state table. It sees the 5-tuple that was created up here and lets the packet path. And then the same happens on router B. Here, packet A comes in. Router B checks its state table and lets the packet pass. And that is the moment where you do hole punching. So basically, you assume this is the place where the hole was punched into your firewall, and then later on, the packet from B could use that hole to get to A. Cool? Okay, you can already see that that's pretty brittle in the sense that you need to connect to each other at the same time. All right, so we added hole punching support to libp2p, and I think the motivation is clear, right? We want 2 laptops or 2 phones or 2 devices to connect to each other, even though there are firewalls and NATs in between. And that in a peer-to-peer network allows us to have pretty much every node reach out to every other node, which is fantastic and has like huge impacts, for example, for IPFS and so on. Requirements for libp2p was no central infrastructure. For those familiar with ICE and turn, ICE, it uses turn and stun, and those are usually in central places, so that's not an option for libp2p. Then we want this to work on Quick and TCP, and potentially we're currently investigating how we can do that with WebRTC as well. And then it should nicely integrate into the libp2p stack. Yeah, let me do the status first. So we set out, like, this has been a long endeavor within the libp2p space. It has been implemented and spec'd, so all of this is specified in the libp2p specification, and implemented in the Go and Rust implementation. I think Go was, as always, far ahead, releasing this end of last year, and then Rust released this earlier this year. So you have the support in the Go, libp2p, and Rust libp2p implementations. And preliminary results show, like, on TCP and Quick, so at least on Quick, you have roughly 90% success rate. And may I remind you, like, synchronizing two nodes to connect to each other at the same time, 90% success rate, that's really, really cool. And yeah, we'll see how we got there. Another things, a couple of things around status. So implemented Go and Rust. It's included in IPFS. Every public IPFS node with the most recent version acts as a relay node. And then every non-public node, soon, not yet rolled out, will be able to hole punch via those public nodes at some point. And then we have a bunch of large measurements for that to talk to Dennis and Elena over there around how we're going to measure that and thus have large data on how hole punching success rates works across the entire network, internet. So that's really cool going forward. All right, so how do we do all of that? So how do we do hole punching in the first place? So synchronize to make sure we connect at the same time, whatever time is. And also, how do we do that in a decentralized fashion? And I want to go through that step by step. I don't think we have a lot of time, so reach out to me afterwards to learn more or dive deeper into specific things. I want to explain that in two phases. Again, we have A and B trying to connect to each other. First phase is B, kind of like preparing to be hole punched to. And then later on, phase 2 is A connecting to B, and then coordinating the hole punch and actually doing the hole punch. All right, let's see. So in terms of complexity, that is the basic flowchart. We'll go through a couple of things. Don't worry, I deleted most of the flowcharts. And yeah, we'll just go through this step by step. So first phase, as I said, B is preparing to be hole punched to. First step in phase 1 is to determine whether one is dialable in the first place and how one is dialable. So we have two different protocols here. On the one hand, we have identify. If I connect to another node, that node will be so kind and tell me what IP address they observe me at. So I can learn my public IP address. That is relevant for NATs, to traverse NATs, as like NATs, again, will map your private or local IP address to a public IP address. Same with ports, but I'll skip that complexity for now. Then second protocol is AutoNAT. You basically ask another peer, hey, by the way, this is my public IP address, or this is what I think is my public IP address and port. Can you try dialing me, right? I don't know whether I'm public or not, whether I'm reachable from the outside, whether I need hole punching. Can you just try? And then the other peer will basically say, yeah, I'm able to connect to you directly, no hole punching needed, so you're public, or no, connection failed, you're probably private, or behind NAT firewall or some other problems. All right, so in the case of succeeding, someone can just reach out to you. You're done, right? No hole punching needed. Don't do hole punching if you don't need to. In case it fails, you need to find some way for another peer to contact you, even though they cannot contact you. So what we do here is we use relay nodes. And as I said earlier, every public IPFS node acts as a relay node in a limited fashion, so it's not a lot of load on them. What I would do if I am behind a firewall NAT, I would connect to one of those relay nodes and basically say, hey, no one can reach out to me, or no one can establish a connection to me, but I still want them to be able to hole punch through to me. So could you kind of like listen on the network, and in case someone has a message for me, forward that message to me, right? So what I would do is I would contact multiple relays in the public network. It heavily depends on which network. For example, IPFS. Our strategy is you take the 20 locally closest peers, and then you choose a subset of those based on latency and ask those to act as your relay nodes. And the last one is you contact each of those relays. You ask them, hey, please listen in case someone wants to reach out to me, forward it to me. You keep that connection to the relay alive. Because again, no one can establish a connection to you. So in case the relay has something to tell you, like it has no way to establish that connection to you. So you better keep your original connection alive. And next step, you can advertise to the network, basically saying, I'm not directly dialable, but in case you want to reach me, right? This kind relay here volunteers to forward messages to me. And basically, you just have to connect to that relay and ask for my PID. And then the relay will be so kind and forward messages. OK, cool. So you advertise that address, last step. Phase 2, another node wants to reach out to me, right? In this case, A. Right? It somehow discovered the relayed address that I was talking about earlier, the bottom one here. And what it will do, first connect to the relay. It has the relay address in that address that I shared on the bottom earlier. A will connect to the relay, establish a connection, and ask the relay, hey, can you relay a connection to the node that I'm actually interested in B? The relay it still has that connection open. B left it open. It will forward the request to B. B basically accepts it, and then from there on, A and B can connect, can talk in a relayed fashion. And this is already pretty good. A and B can now talk over a NAT and a firewall, but there's no hole punching involved, right? Every packet is relayed over that relay node. And now comes the magic, this mechanism of synchronizing time, of having A and B connect to each other at the same time, whatever time means. What we do, remember, A and B have that relayed connection, right? They can talk over that. What A does, it sends a connect message to B with the addresses that it thinks it's connectable via. And B does the same back to A. But A does something cool along the way. It measures the round trip, right? So it measures how long does it take for me to send a connect to B and for B to respond with a connect back, right? At this point, A knows the round trip time. B doesn't need to know it. And what A will do is it will send a sync message to B. It knows the round trip time, so it knows how long half the round trip time is, right? So A knows when, approximation obviously, when the packet will arrive at B. And what A will do is after half the round trip time, so after half the time after it sent the sync message, it will try to connect to B. And then B, as soon as it receives the sync packet, it will try to connect to A. And if you do the math, they will try to establish a connection at the same time. And then as a small reminder, this is the earlier one. They're now connecting at the same time. So as they are sending their packet at the same time out, they're each establishing a 5-tuple in their state table. The packets cross-pass somewhere in the internet, say hi to each other. Packet B makes it to router A. Router A checks the state table, sees a 5-tuple in there, and forwards the packet to A, and the same on the B side. And so now A received a packet from B, and B actually received a packet from A. Cool. That's hole punching in a nutshell. Again, simplified very much, especially around ports and different NAT behaviors and so on, and retries and all of that. But basically, the whole thing here. If you want to learn more about this, we wrote a blog post on the IPFS blog. It summarizes most of this kind of like in written form. It's very similar to this talk. And then at the bottom of that blog post, you also have a tutorial, like a hands-on tutorial on how to do that with Rust libp2p. So you can actually try hole punching, I don't know, between you and a friend and so on. Cool. This is all open source. I had this pitch earlier in my first talk yesterday. All of this is open source, right? All of this is documented and spec'd and so on, so you can use it, and we would really appreciate you using it. And also, it is like open for contributions and collaborations, right? We would love for more folks to be involved in that. So if you're interested in that, or if you just have questions, talk to us at the venue. Like, you see people with libp2p shirts, that's usually a good option, or just reach out to random people and have you redirected. We have documentation on all of this. We have a discussion forum that's usually very helpful. Then we have the concrete specification, so if you want to learn about the protocols on a high level, and then if you want to dive into the various implementations, you find those on GitHub as well. And then lastly, if you want to, we have a community call every 2 weeks, every other week, for you to ask questions, but also suggestions or concerns, comments, and so on, or just to say hi. Cool. That's all from my end. I'm a little bit afraid of your questions now. Let's see what you come up with.
Okay, so ask some very hard questions, so the fears are confirmed.
So 2 questions. How big is the gap for that the routers typically store the IP for the routing table before it's validated, and where the hole punching like fails, like a couple milliseconds, or?
Do you mean how long is the 5-tuple stored in the routing table?
Yes.
Okay, yeah. So depends on the protocol. For TCP, the state of the TCP connection is visible for the router, right? So the router sees the sins and acts, right? And so as soon as you, for example, have a reset in there, the router knows to remove that 5-tuple from the routing table, right? So the router doesn't need like random or timed garbage collect. It also needs garbage collection, but not in most cases. But in TCP, it can actually garbage collect the entries based on the messages it receives, right? In UDP, that's a different story. So what you do, I think what I would guess most firewalls and NATs do is simply based on timeouts. Now that's, if I'm not mistaken, that's at least on the order of seconds. So that's not the big problem. There are a couple of problems around this. So one, that 5-tuple might need to match to a certain, it depends on the NAT behavior. Again, usually that's not the problem. And what we do is, for example, for AutoNAT, what I would do is I would constantly keep a connection to some public node, and that would try to keep my 5-tuple in my state table alive, right? So I would, I don't know, for example, constantly ping you as a public server, and that would make my firewall have that 5-tuple be alive, and hopefully allow hole punches on UDP later on. Yeah.
Okay. And the second one was, what do you do if since it's on the order of seconds, this is kind of like a moot point, but if there's an asymmetric latency, so if it takes longer, or if it's shorter to download, and then faster to download and slower to upload, then
the other side.
Yeah, the other side, like, because it's divided by 2 is the sync, right, period, so.
Yeah, so what's really cool is this chart is wrong, right? These 2 should be all the way here, and these 2 should be all the way here, and there is a big gap in between, which is called the internet. So, packet B has to be past this point before packet A arrives, right? But packet B is way closer to this point than packet A. So as long as packet B makes it over this line before packet A, where packet A has way longer path to get there, right? As long as that is the case, the hole punch would succeed.
Okay, so there's a huge margin of error then.
Sorry?
There's a huge margin of error that you can.
Yeah.
Okay.
Great. Another hard question for Max.
Okay. Hi there. Can you go back to the slide that showed the 5 tuples?
Yeah.
So I'm assuming you wanted to avoid talking about ports, right? But I'm assuming that when A sends out a packet, what's important is that the source port in that packet is what B is going to use as the port when it sends its packet. And so part of this initial communication through the relay, A basically needs to inform B that it needs to initiate sending a message using that port. Yeah, I guess that's part of the magic in this thing. I'd have to I'll read the paper. I just wanted to see that if that intuition was right.
That intuition is right.
Okay.
But unfortunately, there are many, many different NAT behaviors, which make this way more complicated. But yeah, I don't think I haven't heard of a NAT which simply, a firewall that simply ignores the port part and simply says, okay, this IP address is communicating out, so I'll let packets in from all ports to that IP address.
No,
I doubt that's the case. Or I haven't seen that in the wild yet. But yeah, it heavily depends. You need to find out, you need to find out your source port, but from the outside, but within the inside.
Right, I understand.
Thank you. Any more questions for Max? Okay, let's thank him again. Thank you a lot.
Thank you very much.